Okay, so today is going to start sort of a new chapter. I guess every day is sort of a new chapter, but sort of a new theme uh, in the course. Uh, because we're going to start talking a little bit more about linear algebraic concepts. Starting today with something called PageRank. Um, uh, and why? Well, in fact, these tools are very useful for analyzing various things we're interested in, things like random walks and graphs and things like this. So one, they come up because they're useful. But two, in just the same way that sort of like, every lecture, I try to pick some randomized algorithm that's fun and interesting, but also teaches you a little probability along the way, gradually accumulating. I also want to do that with some linear algebra and try to teach you a little bit of linear algebra along the way, which I think is very useful. And at least in my experience, this kind of TCS perspective on linear algebra was very different than my kind of undergrad math experience and stuff like this. So I don't know about you, but for me, if I think about like graph algorithms, something in a graph, it gets my imagination churning. Can you do this? Can you do that? You can imagine lots of kind of algorithmic things. Whereas I don't know, linear algebra, when I took it, felt a little mathy and stale. And especially my undergrad linear algebra class was just like, this is how you do Gaussian elimination. Go spend your weekend following these steps. And it wasn't very interesting at all. But when I learned some of the stuff that we'll be doing for the next couple of weeks and I made some connections to algorithms, then I started thinking about matrices a little more combinatorially. What can you do? Can you do this? Can you do that? And that really helped my intuition for linear algebra and made it much more fun for me. So hopefully we can transfer some of that. We'll see. Okay, so all right, so what's our topic of the day? Okay, so this is apparently well, it's a little small. Let me zoom in. A map of the internet. I think maybe from 20 years ago, centered apparently around the main page of Wikipedia. Okay, so at some level, these lines represent some kind of links. I guess links going out or something, and someone visualized it. Okay, so whatever. The World Wide Web. Of course, you know what the World Wide Web is. Now, okay, so this is of course, where Google comes in. Before Google, you had something like Yahoo. This is before you're born. And Yahoo at some level wanted to be like the yellow pages of the internet. So they actually try to organize everything. You got to a front page, there's 10 categories. You click a category like sports, it opens up into multiple sports. You click a sport, you find teams from that sport, so on and so. Okay, but somebody was actually organizing this thing. Um, but the next step would be, Google, which of course you've uh, come to love and stuff. And maybe it's getting replaced now. I'm not sure. This was maybe more compelling a couple of years ago. But nonetheless, okay, so you're Google and you get a search query. Okay. And maybe what's the first thing you would ask? Or even before that. Or yeah, maybe I'll put that. Okay, let's just do that. Yeah, okay, that's exactly what's written. So maybe it's okay. So first is just what are the relevant web pages? Right? So you might like, I don't know, build a huge index, a reverse index of all the vocabulary words. Um, so that you just say, oh, I just had baseball and it give me all the websites with baseball, right? And then okay, good. So that's just a retrieval thing. That's like a database query, just a search. Okay. Now what do you do? Yeah. Now you got to rank them. So next thing you want to figure out is what are the most relevant web pages among some loose matching to get you started. Okay. All right. So this is this question of ranking. How do you rank websites? Right? They're arranged in this graphical structure. Okay. So what is okay, good. This is a ranking question. Uh Especially if you don't know the answer. What are some fun ideas for trying to rank websites? Simple ideas. Okay, well, that's not a thing. That's just a word. Yeah. Well, how much they pay? Yeah, okay, yeah, we're not talking about advertising today. Uh Imagine you time travel to roughly your birth and like we had a better sentiment towards search engines and the internet. Yeah. Linkage ratio. Okay, what do you mean by ratio? There's a numerator and denominator. Okay, so that looks like maybe in degree divided by out degree. Okay, so that's reasonable. Uh, so the higher the better. So in degree makes sense, right? You have high in degree, lots of people are pointing to you. Why is out degree bad? Right now you have large out degree, it's hurting your score, right? Okay. Well, anyways, so I think that's pretty close to idea one, minus the denominator part. But in degree is very natural, right? So you just want to know what is which websites get a lot of other websites pointing to it, and then just tally it up, and the more the better, right? Okay. How can you break this ranking? Yeah. Yes, yes. So you can make a ton of websites that are linking to it, and then maybe okay, that's one bug. Let me suggest one other bug, kind of leading to the next idea, which is also this also treats all the links equally, right? So let's say you're trying to choose a restaurant in the West Lafayette area, and you have one website that says top 10 restaurants in the West Lafayette area. Okay, and you have another list that says top 1,000 restaurants in the West Lafayette area, right? One of these endorsements is hopefully worth more than the other. And given that it's not clear there is 1,000 restaurants in the West Lafayette area, we do think there's at least 10, um, but one has to check. Okay, so not counting dining halls. So okay, so if I wanted to at least address that minor issue, or I don't know if it's minor or not, but that issue, how can I make it so? Because right now, one website with tons of links to other things is giving out billions of points. How can you address that? Okay, we can normalize it. So maybe a second idea is we can reweight it. So that top 10 list of restaurants that gives you 1/10 of a point. That top 1,000 list gives you 1,000th of a point. Okay, but it still doesn't really address the other issue that was brought up, which is I could just make a bunch of bogus websites pointing to me. Yeah. Okay. So how can we try to deal with that? Yeah. Okay. So let me try to unpeel this. So at some level, you're trying to figure out which websites are good and which websites are bad, and we're kind of looking at, oh well, who points to me? And right now, the current issue is out of those guys pointing around, which of those sources are credible and which ones are bogus? So it's a little bit of a cyclic thing. I'm trying to figure out which are the good websites, and I would love to know which are the good websites to figure out which of their links are useful to figure out which are the good websites. Yeah. Weight them by clicks. Well, Google doesn't necessarily have all that click data, at least maybe until they put out Chrome and right. So at some point it becomes very useful for them to make Android and Chrome so that they can track these. But without that, okay, so without tracking clicks, plus whatever, we'll make some bots that click around. Okay, but we have this sort of semi-self-referential issue. I'm trying to figure out which are the best websites. If I knew which are the best websites, I could trust their links to figure out the best websites. Yeah. So let's try that. Okay. So score three. Uh, there's no reason why they should exist, but it looks nice. I'm trying to figure out the score of this particular vertex. Let me go over all of the incoming things. And okay, this website, how valid is this website? What's its score? And let me divide by the out degree so that it's only giving out, a fixed amount of points. Okay. So this at least From a modeling point of view, just a semantic point of view, checks a lot of boxes, right? It's using authority to bestow authority in some kind of self-consistent way, right? So it seems like kind of a nirvana. Um, Now there are some issues with this. For example, is it clear that such scores exist? No. Or can anyone think of something that satisfies this? All zero would satisfy it. That's not very good. Okay. So this would be nice if we can get like a non-zero solution or something, but it's not clear that one exists. Okay. If it did exist, then we can read off the equality as something we like. It makes sense to us. Yeah. Well, so insofar as score 3 is a good score, we can trust it to give a good score to V. But it's not clear that there are values of score 3 and score V for all the vertices where this is always true for everyone. So this for all vertices U and V is a big system of equations. Not all systems of equations have solutions, right? That's why we have things like regression, which is get the closest possible solution, minimizing a sum of errors or something, but squared errors. But in general, there's no reason why this should exist. But from a modeling point of view, it's nice. Yeah. Okay, so one could try to imagine some kind of iterative algorithm, but even then, does it even converge? It's not clear. Um, yeah. Okay, but at least the model is appealing on a basic kind of application level. Okay, so the point is that as great as this looks, it's not clear that such values exist, at least non-trivial ones. You could set them to be all zero, but that's no good, right? Okay, good. Okay, so the main thing in this class is that such scores do exist, and this is what's called PageRank or some variation of this. Okay. All right. So let me establish some notation. So this is sometimes used, whatever. So delta to the v will be all vectors that kind of represent distributions over the vertices. So what does that mean? It's some vector with one entry for every vertex. All the values are non-negative, just like probabilities, and they sum to one, just like probabilities. Okay, sometimes called like the simplex or some probability simplex, but it's delta to the v. If you see delta to the k, that often means this k-dimensional probability thing. Okay, so delta to the v is because I have one entry for every vertex. So this says that for any graph, that means these degrees can vary for different graphs and stuff. But there's always some distribution over the vertices, which has other properties, right? That means everything's positive and sums to one, so it also has this probabilistic interpretation. There's always a distribution that satisfies this system of equations. Okay. Not only that, but if the graph is strongly connected, then x is unique and strictly positive. Every entry will have some, maybe very small, but non-zero value. Yeah. Out degree, number of edges leaving you. So that's the main theorem. It's a math theorem. Okay. And it's almost exact, it's perfect for our application. Oh, give me this magical vector x. That's a nice way to rank websites. This self-consistent way actually exists. Okay, the next question is why? Not all system of equations have solutions. This not only has a solution, but it's non-negative, it's a probability distribution, everything's strictly positive, it's unique. Why? Anyone want to take a stab? So this is the theorem that we're going to spend our class dedicated to proving. But just like, does anyone want to try, but it's sort of a miracle theorem. This particular system of equations has a solution x, and it's very nice. It represents a probability distribution over the vertices. It's also unique. Uniqueness would be very good. If there's multiple ones, then you're like, which one do I choose when I rank the website? Yeah. Uh, It has as many. Well, okay, so it does have n constraints and n variables. Um, but that doesn't necessarily imply there's always a solution. As soon as you have two constraints that contradict each other, that's going to be problematic. The strongly connected is just helping with the uniqueness part. Because at some level, if I had two different graphs that are disconnected, I can have one x here and one x here. And any combination of the two would give me something satisfying the whole thing. Okay. So that's the okay. So it's not because of the strongly connected part. The question is, in a shot, I mean, of course, we're going to prove this thing. It's going to take some effort. But if anyone wants to try to guess why such an x should exist, what's so special about our situation? What characterizes our setup? Yeah. There is a matrix so it is a linear system, which is the same as saying there's a matrix representation. But why does this matrix always have this nice solution? Well, once there's an x, that means it's not overdetermined. Well, uh, for that can have best address the uniqueness, but you can have n linear equations and n variables, but if the linear equations contradict each other, there's no solution, right? So that's not exactly it. If it's full rank and stuff, then you can invert it, but that's not always the case. Yeah. Um, well, there's certainly some nice structure here. It's very particular, but it's not necessarily symmetric. Yeah, it's not because if you go backwards, kind of so to speak, it's also a directed graph, so it can be quite asymmetric. But even an undirected graph, uh, because it is out degree, if the out degrees are different, you'll find that the matrix is asymmetric. Yeah, no, I'm torturing you a bit, but partly because the more you think about it, the more excited you'll be to find out. Yeah, this is an eigenvector with eigenvalue 1. Why is there an eigenvector that's non-negative with eigenvalue 1? That's not always true. It is not necessarily the fixed point of it. It's not because it's a fixed point of iteration. And that also doesn't tell you why it's exactly 1 and positive and things like this. I mean, it's a fixed point in the sense that like once ax is equal to x, then you apply a is always going to get you x again. So that's just what an eigenvector is to some extent, right? But it doesn't tell you why it has all these nice properties. All right, okay. At least we hopefully we appreciate the intrigue. That we're excited. Okay. All right. So a random walk in a graph is the following. You're at a particular vertex and you pick a random edge and you go there. You pick a vertex, you go there. Okay, so you just pick a random edge every time and you follow it. You could have a weighted random walk where the edges are weighted, and then you pick those edges in proportion to the step in proportion to the weight. Okay. So if I like have start with an initial distribution, or I just start at a particular vertex, I take one step and I can choose from 5 possible neighbors equally at random. And I take another step and that branches out more, right? So after 5 steps, there's some distribution over the graph of where I could be. I could be here 10% of the time, 20%, right? So we can, I can write like p to the k as like that distribution over k steps. And the question is, when you take a random walk, does it converge? Or is there maybe like a stable distribution? Is there some distribution p, right? It's like an equilibrium. So it's currently some distribution over the vertices. And if I apply a random step to that distribution, that means for my distribution, I pick a vertex and then I take a random step. And then what's the overall resulting distribution? Will be the same as that first one. Okay. So yeah, so okay, take this graph. Um, very simple graph, of course. It's just a cycle of length 3. What would be a stable distribution in this graph? Okay, if you did 1/3, 1/3, 1/3, okay, in one step, this 1/3 probability mass shifts here. The one-third probability mass shifts there, the one-third probability mass, just cycles around. Okay, so in one random step, starting from here, you'll get back the same thing. Okay. All right, so that's a stationary distribution, is when you reach something where it's a fixed point of the random step. I should point out, maybe a simple thing. It's not, you don't always like achieve the stationary distribution. Let's say you started with one here, then that one goes here, then that one goes here, then that one goes here. You never approach a stationary distribution. You just keep cycling around. All right. So if we go back to here, or maybe I can even look at score, right? This starts to look like a random walk. I'm at a website, I pick a link at random, and I go to that website. I pick a website, pick a link at random, and go to that website, right? And if I'm at a website and say, okay, what are the odds of things coming into me? I go back to all the neighbors. This vertex will pick me as 1 over degree plus. That vertex being 1 over degree out degree. Okay. So what score 3 is really describing is the stationary of some random walk over the internet. Stationary distribution. Okay. All right. So good. Good. All right. So that theorem from before is actually a little more general. It says every random walk on a directed graph has a stationary distribution. And if that graph is strongly connected, then the distribution is unique. Okay. That stationary distribution is the x, is the score 3 that we want. So, but now we've got it down to this theorem. Okay, and this is what we're really trying to prove. Every random walk, that's a natural object to study in a randomized class, has a stationary distribution. Okay. All right. Why? Okay, this is more rhetorical. At some level, it's all going to be linear algebraic phenomenon. Yeah, that itself is sort of interesting. We want to do something on graphs, sort of a combinatorial thing, but we're going to need to use, a new set of tools. Okay, any questions? Yes.
Using the distribution formula to type it before we mention the example of the station.
So, uh,
Yeah, the PV. This slide, right? Yeah. Okay, so
so we're not saying that you always get to the stationary distribution if you start somewhere and start walking around. Like that's this example here, right? You start on one vertex, you go around and around and around, you don't make progress. But this claim is that there always exists a stationary distribution. We'll worry about trying to find it later. Okay. But at least there exists a stationary distribution. There is something for Google to base its search results on. Okay. Yeah.
So I have a question on what you're saying is basically like we start from like one vertex, then we have like a certain vertex, and the probability of going to the one vertex is like some probability.
Yes.
If we have this like loop, then probability like going back around the loop, it becomes like 1 by 3 times 1 by 3 times 1 by 3, which approaches 0.
Okay, so the theorem says that there always exists a stationary distribution, which in this example is 1/3, 1/3, 1/3. So if I put 1/3 probability on each vertex, I take a random walk, it'll keep the exact same.
It'll keep the exact same.
Yeah, so let's say I have 1/3 mass here, 1/3 mass one, and I do one step of the random walk, and I look at the resulting distribution, I'll get the same 1/3, 1/3, 1/3. Cause I just take one step, right? So this 1/3 goes up there, that 1/3 goes here, and this 1/3 goes here. So you end up with 1/3 everywhere again.
And if it includes anything other than 1/3, that will not work, right?
That's right. The theorem also says it's unique. Yeah.
this theorem doesn't say anything about arriving at a stationary
It
distribution.
doesn't say anything about arriving.
Just
Yeah.
you state this.
Yeah, so questions like converging to a stationary distribution, that's going to be more in future lectures. Google has a hack that makes it very easy to arrive at their stationary distribution, so it's not very deep at all.
Depend on the starting vertex, right? Like for convergence.
Yeah, it depends a lot on the starting vertex or the style of the graph and things like this. We'll be discussing random walks a lot for the next few weeks. Yeah, but this is just a starting point. Even the existence of a stationary distribution, that's a place to start.
Skipping the DNF.
Yeah, the DNF lecture like takes 10 minutes, so I can't like, yeah. Okay. Okay, so let me do some linear algebra. I teach you some linear algebra, and the goal is like, oh, if we learn some linear algebra, maybe this will come out almost for free. Okay. All right, so I think you guys all know this because we've done it already in this class. It's like Johnson-Lindenstrauss. You know, a linear function f of x is, you know, f of x plus y is f of x plus f of y. F of 10x is 10 of f of x. Okay. So those are at some level the easiest, simplest possible function in mathematics. And at some level, I think one of the themes that I pull out is like, if you kind of restrict to this very simple class of math, right? It's the simplest possible thing. You just add and subtract and multiply, scale. You can actually say a lot about it. And you couldn't say if you are trying to capture all functions and stuff. So, for example, any linear function you can always express as a matrix. So if you have an f, you could write it as aij. Okay. I often actually don't think of the matrix explicitly. I just think of kind of the algebraic properties, but yeah. Okay. All right, so good. All right, so we have first an adjacency matrix to try to model a graph. Okay, I'm going to do something that's going to kind of transpose what you're used to because I want to keep the inputs on the right, so to speak. But AVU, which is sort of like U going to V. Okay, so that'll be 1 if UV is in the graph and 0 otherwise. Okay, you're probably used to the opposite because normally you have rows and it has the neighbors. This will have columns and list of neighbors. This way, it's very easy to write things like AX in the way you'd expect. Okay. All right. So for example, if I wanted to express score 1, which is just the in degree of each vertex, in terms of this adjacency matrix A, or transpose of, how could we write that? Just as like a warm up. So V is a vertex. So when you say AV, oh, AE sub V, yeah, A times the 1 vector. Oh no. Okay, let's try to do this. A times the 1's vector, that's going to, you know, if I look at the, yeah, so 1's is coming on the inside, on the input side, right? It's going down a particular column, which is for a vertex U, lists all of its neighbors, and it distributes that 1 to all of its neighbors. Okay. All right, so that's not too big a deal. What would be the out degree in terms of A? Just as another warm up, make sure we're on the same page. Yeah, 1 transpose, which I wrote like this, which is the same. Okay. All right. So E sub U, that's like the indicator vector for U. That means 0 everywhere, but 1 for the elementary basis vector, whatever nonsense. Okay. Good. All right. So now working up to the random walk matrix. Suppose I let D be a diagonal matrix that lists all the out degrees on the diagonal. Okay, so it looks like you have an n by n matrix or v by v matrix kind of thing. And you know, you just have the out degree of each vertex along the diagonal. So everything else is 0. Okay. So then the random walk matrix is going to be RA D inverse. So D inverse is going to give you that 1 divided by out degree stuff. Okay. So at some level, when you pass in the 1, it gets split up into the out degree and ends up distributing that equally to everything. If you want to do the algebra fast, I don't think everyone wants to watch me do linear algebra all day. say, okay, this if this is a random walk matrix, this should be the probability of u going to v. Okay. Or if you want to write it in terms of like coordinates, it'll be r du. And okay, if you expand that out, it'll look something like this. Okay. And then if we just plug that in, it's a vu divided by out degree. So that's a 1 if there's an edge and 0 if there's not. Okay, and that's exactly the probability of u going to v in the random walk. Okay, so that's all fine and dandy. At some level, we haven't done anything too deep. All right, in terms of score 2, I can write score 2 as something like what was score 2? I don't. Oh, it's divided by the out degree, right? Score 2 was divided by the out degree. Okay, good. So R is doing that division. Otherwise, it's treating all of the websites equally. That's why you have the all ones. Okay, so for a particular vertex, that's like a row, and I'm going through all the inputs. This vertex has a link, out degree 10, it'll send 1 over 10 over to this. Okay, things like this. And with respect to R, the stationary distribution is a vector x that satisfies x equals Rx. Okay, that's also positive and non-zero and stuff like this. Okay, I know you guys are super excited. All right, so the key point is that that x is equal to Rx for a stationary distribution. And that happens sometimes when ax equal to lambda x for some scalar lambda. In our case, lambda is 1. All right, do we remember what this is called? Eigenvector and eigenvalue. Okay, the scalar value is called the eigenvalue. The vector is called the eigenvector. So presumably most of you have probably seen this before. Not necessarily everyone each year. Okay, so, okay, good. So now let me state the theorem again, but in a slightly more mathematical language. Let G be a directed graph and let R be the random walk linear map associated with G. Okay, the matrix. Then R has an eigenvector, X, that's in the probability distribution over vertices. So this is doing a lot in a small notation with eigenvalue 1. Okay. And if G is strongly connected, then X is a unique eigenvector with eigenvalue 1. Okay. So stationary distribution is some kind of eigenvector that was already kind of previously mentioned. What's important about this theorem is the nature of the eigenvector. The fact that the eigenvalue is 1, the fact that the eigenvector is non-negative and sums to 1, right? In general, even that it's real valued, you can't take for granted. Same with the eigenvalue, right? Okay, good. All right, so it comes all down to this eigenvalue, eigenvector nonsense that I'm sure you've at least heard of before. It might bring back exciting memories of some math class you took. So as we bring back memories, does anyone know how to prove that every linear map has an eigenvector and eigenvalue?
Just the fundamental theorem of algebra.
Okay, how do you prove it was a fundamental theorem of algebras?
Like the eigen values, you do like the determinant of blah blah blah, and then so
Okay, so I think you guys, this is some very painful thing, but what you're looking for is something where like a minus I lambda has has a map vector that maps to 0, and somehow you learn that like the determinant is somehow related to this. Okay, and if you remember that this is like an insane way to try to prove this, absolutely insane. You know how painful it is to write out and define the determinant. Well, it takes a long time. You have to over all the permutations, you multiply them together. It's n to the n. What the you would never yeah.
What's funny, see, I didn't
What's what? Yeah, that C is for complex. Okay. All right. Anyone know a better proof than this determinant nonsense? Which is yeah. Okay. Oh. All right. Here's a better proof. Okay, that sounds like a subjective thing, but I think you all uniformly agree in just a moment. Okay, so let's take any vector, the non-zero vector v. Okay, and then you have like oh shoot, it didn't go well. All right, so you have the vector v. You have the vector av. Okay, you have a square v. You can do aqv. You can keep applying this, right? And let's generate, I don't know, n of them. N plus 1 including v. Okay, so you have these n plus 1 vectors, and what can you say about them in n-dimensional space? Yeah, they're linearly dependent. Maybe you saw that for a flash of a moment, but they're linearly dependent. Okay, what does that mean? That means there's some coefficients that are not all zero. Alpha 0, alpha 1, alpha n. Sorry? It's an alpha. Okay. And if, yeah. Okay, something like this, right? Okay, so good. So what does that mean? That means that there's some polynomial induced by the alphas where P of A times V is equal to 0, right? What is that polynomial? That polynomial is, would be, P of x is equal to alpha 0 plus alpha 1x plus alpha 2x squared plus alpha 3x cubed and things like this. Yeah. Because if you have n plus 1 vectors in n-dimensional space, there's some linear dependencies. They can't all be linearly independent. Okay, so I assume that fact. But that's much more modest than what is a determinant. Okay. All right, so there's some polynomial. That's what the alphas give you the coefficient of some polynomial where P of AV is equal to 0. Okay. All right, now what do we know about polynomials of degree n? They have n roots, right? So now here comes your fundamental theorem of algebra. There's n complex roots. Okay. So P of x is of that form for some R1 through Rn. Okay. You still with me? And okay, now if I apply that to this, right? What does that really say? I thought it said something. Oh, I'm supposed to write this myself, I think. Okay, so what you do is you interpret those R1s as R1i's. So you get A minus R1i, A minus R2i, A minus Rn I applied to V is equal to 0. Okay, so what's the last step?
One of them is zero.
One of what? So maybe this one is 0, right? Maybe A minus, we know that by the time I get from here and process all of them, I'll get to 0. Okay, so let's look at the first one. If it's 0, then Rn is our eigenvalue. Okay, but if not, then this is some V1 or something, right? It's some non-zero. So now I look at the next one. Is the next one 0? Or I apply one more to V1. If it is, then I have my eigenvalue, and V1 is actually your eigenvector. Okay. If not, okay, you keep going. You keep going. By the end, you have to get at least one of these to come out 0. That's your eigenvalue and eigenvector. Yeah. Okay. All right. Everyone okay with that proof?
I didn't use a determinant. Like maybe just no.
Well, you're wrong. Okay. Good. So, okay. So we know that everything has a complex eigenvector. All right. So for the next part, we're basically going to keep learning about eigenvectors and eigenvalues until it's like, oh, now I understand Markov chains. Okay, so transpose, I think you guys notice when you kind of rotate the thing. In terms of my beloved kind of inner product notation, you can define it as xay is equal to atxy. It's sort of the unique at where that holds for all xy. Okay? All right, so here's a nice lemma. It says that A is invertible if and only if A transpose is invertible. Why? Try to do it without a determinant. Which is, I don't know why you use a determinant, but if you,
is equal to A inverse.
well, assume you don't, well, remember, you don't know if A transpose inverse exists. That's the question.
Yeah, so like, well, if A inverse doesn't exist, then it would like A exists only if A inverses, because it's equal to A inverse.
Just transpose the A times A inverse.
Transpose A times A inverse.
Oh yeah.
Inverse of
A inverse is equal to
Okay. Okay, so we know that's equal to I. I can transpose each one. Okay. Do you remember what happens here?
A.
So this will actually get switched in order,
So then, well, yeah.
something like this. And then I transposes I. Okay, so you have, okay, that's one way to do it. All right, so that's useful. That's simple. Okay, next claim. A and A transpose have the same eigenvalues with the same multiplicities. Why? Well, because the eigenvalues aren't unique. Like the eigenvalue 2 can appear 5 times. I'm just saying if it appears 5 times for one, it's going to appear 5 times for the other. So like the multi-set of eigenvalues is the exact same. From first principles. Everything we've been doing has been from first principles. I guess I assume that n+1 vectors make a linear combination, but beyond that. Yeah. Yeah, yeah. So if okay, then I think say ax equals to lambda x, then I can take a transpose of both sides. Something like this. Although it gets a little bit tricky because now you have xt at is equal to lambda xt. And what you're really interested in is things like aty applied on the right. But here's maybe something that's kind of similar in spirit. So lambda is an eigenvalue if and only if a minus lambda I is not invertible. Right? Because you know that whatever the eigenvector is, this goes to 0. Right? So it's not invertible. Multiple things are getting mapped to 0. Okay. Okay, and now from this, if I look at the transpose, then you get A transpose minus lambda I transpose that's equal to I again. Okay, so as a result, the same values A and A transpose is going to be the same values that make it invertible or non-invertible. Yeah, so you end up with the same eigenvalues. Okay, sound good? All right, good. Oh, okay. All right, now here comes the mother of a theorem. Okay, now all this was like warm up. Okay, well let me first start with the condition. Okay, so we're not going to analyze random walks right away. We're going to do something a little bit more general. Okay, let A be a linear map that's positive, not in a positive semi-definite sense. I mean, like literally every entry is positive. Okay, one way to write that, I always try to avoid like Aij stuff, is saying that if you take any non-zero and non-negative vectors x and y, and you take the inner product over x, a, y, you always get something greater than 0. Of course, if you do like ei, ej, then you'll conclude that every entry is 0. But I try not to think about entries. Okay. All right, so everything is strictly positive. Okay, which is actually not true of our random walk matrix because there we actually have some zeros if there's no edge there. Okay. All right, let me go through this. Okay, so if A has all positive entries, it's positive in this very strong sense of the word. Okay, then you know the following. It has an eigenvalue lambda 1, and an eigenvector x1. Of course, that all matrices do. What's interesting is that lambda 1 is always going to be greater than 0. Okay? And the eigenvector is also going to be strictly positive. Every entry will be positive. Okay? X1 is a unique eigenvector of lambda 1. It's starting to look like that stationary distribution theorem. X1 is a unique non-negative vector so that AX1 is at least lambda 1 x1, kind of coordinate-wise. It's equal, but it's also the only one with greater than equal coordinate-wise. All other eigenvalues have absolute value less than lambda 1. Okay? And all the other eigenvectors have at least one negative entry.
Or they can also be complex.
I think this might be positive.
Do we know that A has all three of them? So it's complex numbers I thought will order.
I should have said something. Let's just assume they're real. That's the only way this makes sense. I think this is also real. I should have probably stated that somewhere, but it's okay. All right. What we're really focused though is on lambda 1 anyway. Okay. And so the fact that you even have a single positive eigenvalue is already exciting. It is the dominant eigenvalue in the sense that all other things, whether it turns out to be complex or not, are smaller than lambda 1 in terms of magnitude. And no other eigenvectors are kind of all positive. Okay. Maybe it does allow for complex and just saying all positive. I shouldn't have said one negative coordinate. Maybe just saying they're all positive. Yeah.
What does it mean by like eigenvectors or it's like
All the coordinates are non-negative, are positive real numbers. Oh, okay. Or every eigenvector has to have a mix. No, okay. So it's saying that no, it's just saying no other eigenvector is all positive. Yeah. So here we're treating x and negative x as effectively equivalent. Yeah, but in general, no other eigenvector. So this is also up to scaling, right? Like at some level, like you could say there's multiple x is not unique because x and 10x are both eigenvectors, but we're treating that as equivalent. Yeah. So in some sense, if you don't take care of those simple things, then there's no such thing as a unique eigenvector. So you do kind of modulo the obvious things. Okay. So this is called the Frobenius theorem. It's really saying, look, at some level, a matrix in and of itself is just a mumbo jumbo of numbers. There's not much structure, not much what you can say. This is saying that if you give me some conditions on A, in this case, all the entries are strictly positive, then I can tell you a lot about the eigenvalues and eigenvectors of this particular mumbo jumbo of numbers. There is, in fact, a lot of structure there. Okay, and that's going to be kind of a theme in the next couple of weeks. It's more than just a grid of numbers. Okay. All right, so how do you prove this? So this is a little bit of more of a mathy proof, or at least I learned it from more of a mathy place. Okay. So it's going to be not as constructive of a proof or directive of a proof as we usually do. So a little topology. So, but it's sort of a trick proof. So I'm going to first create this set L. Okay. And it's going to be the set of all values lambda. Okay. Such that AX is greater than or equal to lambda x for some distribution x. Okay. It feels a little technical, it feels a little eccentric. The theorem we're proving is technical and eccentric. And at some level, what we're going to try to show is that the supremum of this set, which we know nothing about, we don't even know that supremum exists, is the eigenvalue we seek. Yeah. Yeah, this is every coordinate being bigger. Okay, so one vector is greater than another if just every coordinate is greater than equal. Okay.
Is there a distribution that delta
Delta n is the set of distributions over n. Okay, so it's not any x, it's just some subset of x. Okay, it's a weird setup, but somehow this works. Okay. Okay, so yeah, maybe I should warn you. So some of this will be like a little mathy, technical, but then afterwards we'll also apply it to random graphs. So if you shut off for the next 10 minutes because we're just doing like a proof, we'll still come back and try to use it and hopefully build some intuition for this theorem. Okay, but might also be good to see this thing get proven, at least to some extent. I think I'm not going to prove all of it. I just want to prove that lambda 1 and x1 exist. I won't do uniqueness because that takes forever. Okay. All right. So, but the setup is already a little different than we're used to. I generate some set, and I'm going to try to prove some properties, and I'll take out the supremum and show that's what we're looking for. It's a little magical. Okay. So the first claim is that L is non-empty. So all we have to do is come up with some value and that it exists. Yeah.
Just take x to be like e1, and then that'll be like a formula guy.
Okay, so if you take x to be e1, right, then a e1, if I think of a as like a big thing, e1, you're just putting 1 down this particular column, right? But there may be arbitrary rows. This is some other, e1 would have been the first column, but this could be like the 5th column and the 10th column, right? So you need every coordinate to be bigger. But there might be 0 in the first column. Huh? Oh, a is a strictly positive. Okay, that's true. Okay, that's fine. Okay, so you'll get something, right? You'll get whatever's A11. Okay, good. I was thinking ahead. All right, so that's fine. So if I, for example, take x to be E1, then AE1 is equal to A11 E1. Or it's greater than A11 E1, because that's what you get just from the first row. So you can take lambda to be A11. Okay, good. So it's not empty. That's a start. Okay, nice and simple. What? A11? Lambda is equal to. Oh. Sorry. So. Okay. So one sec. If I put this one here, isn't that okay? Is this what am I missing? Isn't AE1 greater than equal to lambda E1 for A11? I'm not trying to get the best lambda ever. I'm just trying to show there's at least one lambda in this set first. That's the indicator vector. You have a 1 and a bunch of zeros. E5 would have the 1 in the 5th slot. Okay. All right, next one. The claim is that L is bounded. How do we do this? Okay. Okay, so let's say that you have some value in here, right? Then you know that AX is greater than equal to lambda X. Okay, and like you said, I can set X to be the all ones vector, right? So I know that kind of lambda, oh wait, no, it's for some X. Okay, so we know that lambda X, okay, one sec. We have to be a little bit careful, right? So you want to show that lambda X is less than equal to, or all we know is lambda X is less than equal to AX. So why can we not make lambda arbitrarily big? Yeah, right. So we just need a simple upper bound for AX or something, right? Okay. So one sec. So this is okay, so this is less than equal to A all ones. Okay. And then meanwhile, here that the maximum coordinate, if I take the maximum coordinate over all I of lambda xi, this will be at least lambda over n. Because one of those entries xi has to have at least 1 over n because it all adds up to 1. That's the other half you need. Okay, so then if you know that lambda over n is less than equal to kind of A1's kind of thing, that'll give you some bound. Okay, just some upper bound. All right, so that means that the supremum is going to be finite. But this one last part's a little bit tricky. So what I want to do is I want to be able to take the supremum, but also have it come from L. And to do that, we need to show that it's closed. What does closed mean?
you take the sequence,
It means sorry.
the sequence from the set, then the limit point must also be in the set.
Yeah. So if well, in particular, if you have a sequence that converges to a point, you want to make sure that point is in your set. That's the definition of closed. So it's only for converging sequences, right? Okay. Boy, sarcastic math is something else. Okay. So good. I had something written here. Okay. So I want to show it's closed. So let's say now this is the sequence of values, right? So suppose I have a bunch of values. This is gradually approaching some value lambda bar. Okay, so it's getting closer and closer and closer. I want to show that lambda bar is also in our set L. That means I need to find some vector x that satisfies it. Yeah.
Why are these values approaching
No, what we need to show is that if you have a sequence of values in L that approach some value or converging to some value, that value, that limiting value, must be in your set L. That's the definition of closed. Okay, for all the math heads out here. Okay. All right, so how do you do this? Well, what do we know about the lambda 1, lambda 2s? They're in L. What does that mean? Okay, there's some x, right? So for each I, you have some point in the simplex is axi squared and equal to lambda ix, right? Okay, and then what? Isn't it exciting to use all your analysis skills out in the wild? You've been waiting for this day for like
Is this a monotone sequence?
it's not a monotone sequence.
You know it's bounded below, so it has to be monotone, right?
This is some sequence over.
Yeah. Ah, okay. What was the name of this again? Yeah. You remember the name? Yeah, Bolzano-Weierstrass. So it's compact. The simplex. So we don't know much about L. L is a mysterious thing, but we know this thing where everything sums to 1 and is non-negative. It's compact, and so the Bolzano-Weierstrass says there's some subsequence that converges to some point in the set. Okay. Bolzano-Weierstrass is just you keep splitting in half, keep splitting in half. One half has infinite many terms in a sequence until you get arbitrarily small space. Right? That's how I remember it. Okay. Okay, so this thing is compact, and what does that tell you? There's some subsequence that converges to some x in the simplex. It's a subsequence. It only tells you there's a subsequence. There's an I sub 1. That's easier to see, maybe. Okay. All right. So that, whatever, for the people who are doing math out there. And I thought I had something written there, but that's okay. So, sorry? The limit if I look at the limit of the subsequence, right? So ax bar is going to be the limit of this subsequence, and these are all bigger than your subsequence values. Yeah, and this will, in the limit, also get you to lambda bar x bar. Okay, so x bar is going to be your evidence for lambda bar being in the set. Okay, so that was super fun to do, like a little bit of some delta epsilon style proofs. Now, huh?
So just to clarify, we know that delta n is closed and bounded, right?
Yes. So it's compact.
Yeah.
Okay.
We kind of forgot it.
I mean, granted, I haven't like taken this that seriously in like 20 years, but like, you know, some stuff you don't forget. Okay. All right. So, okay, now finally what we're going to do is we're going to take lambda to be the supreme of L. That means the least upper bound, right? And the point of all this kind of accounting we just did is that it exists, okay, and it's finite because it's bounded. It's finite, and it's in our set L. Okay, so all that little kind of topology we did makes it very nice to pull out the supremum. And that means there's some vector inside where ax1 is greater than or equal to lambda 1 x1. So this set has a unique kind of biggest element, and it satisfies those same rules. And ultimately, we're going to show that x1 is that vector we're looking for. Okay. I'll do it quickly. I think it's prepped. All right, so the claim is that they're actually equal. Okay. And then that will at least satisfy the first part of the theorem. Okay, so suppose not. If they're not equal, then I know that ax1 is equal to lambda1 x1 plus some vector y that's non-zero. Okay, so if ax is strictly bigger than, it's bigger in some coordinate, then y will be a non-zero vector. Okay, so y is some kind of padding. So, okay, I don't know, maybe it's a trick proof. But choose epsilon so that epsilon divided by 1 minus epsilon is equal to the sum of y coordinates. Okay, so if it's really small, you can make epsilon really small. If it's really big, you can make epsilon approach 1, and it'll be arbitrarily big. Okay? There's some value epsilon making this work. And if I shift x1 down by epsilon, and then think of this as normalizing y, so I add back an epsilon fraction, I'll get another distribution. Okay. Now let's look at some level, this is going to be our contradictory vector. So, oops. All right, so let's look at this, right? And this is at least I can just drop this term y. Oh, I shouldn't have wrote in delta n, but just copying and pasting. Okay, why is this?
Looks like 0. That's all right.
Yeah, so this is positive, so that we're only dropping a positive term here. It's also strictly positive. All right, and now what do I know about ax1? 1 minus epsilon a of, or this thing. Oops. Yeah, something like this. Okay, and then what do I know about this? What do I know about this? Okay, so let's put the lambda 1 on the inside. So let's first go like this. 1 minus epsilon x1 plus 1 minus epsilon y. Yeah, something like this. So what's 1 minus epsilon equal to? 1 minus epsilon is equal to epsilon over 1's y. All right, so we plug this thing in. Lambda 1, 1 minus epsilon x1 plus, so we recover what we just had. Okay, so these two terms are equal. One was written ahead of time in better handwriting, the other one was written live. Okay, but this is equal to this, and we have a strictly greater. So I could actually afford to make lambda 1 slightly bigger. But lambda 1 is supposed to be the biggest possible thing. So that's our contradiction. Okay. All right, so much for that. All right, so that's some of the proof of this amazing theorem. Let's now, in the brief time that remains, go back to random walks. Okay, so pro Frobenius, I only proved the first part, but I had more to it. Everything's strictly positive. You have uniqueness and all other eigenvalues and things like this. It's in the notes. Now, let's go finally back to random walks, and that'll be our closing point. Okay. All right. So let's say that R is now modeling the random walk map on a strongly connected graph. Okay. So this is all we're looking for, right? There is an eigenvector that's in the distribution with eigenvalue 1. That was the original claim, but we have more. X is a unique eigenvector with eigenvalue 1. X is the only non-negative eigenvector, and other eigenvalues have smaller magnitude. This will be particularly useful in future lectures, the smaller magnitude part. Okay. All right. So the real question is, how do we apply our theorem with where everything's strictly positive to a random walk matrix. So I think there's maybe two things that are a little bit different. One is that R is not all strictly positive because R has zeros because you don't have edges everywhere. And the other thing is that our theorem before did not tell us that the eigenvalue is going to be 1. Okay, so that's also something that we'll need to address. So there are two main things. How do I apply a theorem that's for strictly positive to a random graph, random walk that's not all strictly positive? All the entries are non-negative, but they're not strictly positive. And how are we going to pull out the eigenvalue 1? Actually, that turns out to have a cute trick. But let's start with the first question. How can I apply my strictly positive theorem to this non-negative matrix? Yeah.
R to the n is strictly positive enough.
R can be what?
R to the n. Is it R to the n is strictly positive?
R to the n. So what does that look like? That looks like n steps on a random walk. Well, you have to be a little careful. Let's say you have a cycle. R squared is the same cycle. Or you're just moving 2 stops over. R cubed represents going 3 stops over. R to the fourth. So R to the n is going to be like actually maybe the identity matrix, or R to n minus 1's identity matrix. In any case, you're not getting all filled in. It's going to be one thing. So it's not quite R to the n, but that's a great idea. Can I transform R to make it strictly positive? Yeah.
Epsilon greater than 0 by 3 normalized.
Oh, can I try to add a small edge and then maybe take the limit? That maybe could have worked too. But I didn't write it that way. You have to be a little bit careful about taking limits. Yeah.
Right, plus or minus 1 plus.
Oh, okay. So something that looks like this. So this is the average of taking 1, 0, 2, 3, 4, however many steps. Why is this strictly positive? Strongly connected. So for any two vertices, there's some path to get there. Let's say it has 20 edges in that path, then R20 will have some non-zero value. Okay. All right, so you do that, everything becomes strictly positive. And I think you guys already kind of, at least the people volunteering, already sense this. An eigenvalue of R, what does it corresponds to what kind of eigenvalue for Q? For this particular Q. Yeah. Yeah, so it'll be this kind of same powers. All right, so the eigenvalues are basically in kind of one-to-one correspondence. This is also going to play nice with, 1 is going to stay 1, which is very nice. And things smaller than 1 will stay smaller than 1. Okay, now, okay, so you guys already figured that out? All right, so I think one big question remaining is why is eigenvalue 1 going to pop out? Anyone? Yeah.
Since matrix is like stochastic of one sort of like ability being effectively I guess.
You have to be a little bit more careful than that, I think. Because that could be set of many vectors besides the stationary distribution or something, right? Well, okay, let's see if any other ideas basically at some level. I think there's some simpler, maybe trick way to go about it. Let's see what's coming up. Okay. All right, so you have this, you have some eigenvalue, you have some eigenvector strictly greater than 0. Of course, you can normalize it to be a probability distribution. The question is, why is lambda 1 equal to 1? Okay. So let's look at Q transpose. Yeah, it's a random walk, or any random walk. Q is also a random walk, right? Of some graph. What happens when you do Q transpose all ones? So in a random walk, all the columns sum up to 1. So then if I send 1 through the rows, a column is going to accumulate 1. Okay. And if you look at the Frobenius theorem applied to Q transpose, right? Because that showed that there's a unique non-negative eigenvector corresponding to that dominant eigenvalue. If you apply Frobenius to Q transpose, you'll get that 1 is the unique dominant eigenvector with eigenvalue 1. Sorry? For Q transpose. So we just showed that for Q transpose of 1 is equal to all ones, and that you can just read off. That's true of any random walk matrix, right? Okay, well, now the claim is that that 1 is the dominant eigenvalue for Q. Why? Oh, the little, yeah, okay. Yeah, so Q and Q transpose have the same eigenvalues and the same eigenvectors, or same eigenvalues, the same multiplicities. Okay, so we know then that the biggest eigenvalue for Q has to correspond to the biggest eigenvalue for Q transpose. That's 1. That makes x1 the stationary distribution, and all that rest follows from the Perot-Frobenius theorem. Okay, so there's just some cute tricks to apply the strictly positive theorem to random walks. Okay, so it's a little bit delicate. I also didn't go through all the uniqueness and stuff, which is a little more analysis in the same style we just did, kind of less CSE. But it's a nice example of how some linear algebraic structure actually gets you something very useful. Okay, maybe in closing, I'll note that the Google PageRank was even did an even simpler random walk. Let me give you a slightly off, but like you can imagine a random walk like this. You're at a random vertex, and say with probability 95% you'll go to a random out neighbor, or with probability 5% you'll restart and start at a completely random vertex. Okay, or in the case of something like Google, they might just start at yahoo.com. So just restart to like a trustworthy website, and they'll just restart the random walk there. And so the random walk will really kind of reflect some kind of authority that's rooted at Yahoo and maybe a couple other websites. Okay, you can show that this kind of random walk will actually converge pretty fast by studying the gap in certain eigenvalues, and we'll do something analogous to that for other topics in upcoming lectures. Okay, so they modeled this random walk. They had this random restart, and that actually converges very fast. So you can just simulate the random walk. It converges pretty fast. It's very simple computation, so you can distribute it over many machines. Okay.